Clean up a little bit the next set of lecture notes. I'll post them soon. We'll have the final project will be distributed next Tuesday, and I'll discuss that with you, and you'll have a little over 3 weeks to do it, and it's more than enough time. It's about as long as one of our problem sets. So maybe you need more than 3 weeks to be nice. All right, we'll discuss that more next week. All right, so let's see. So what we noted last time was that when we were looking at the damp simple harmonic oscillator, what we found is that the equation of motion for the quasi-probability distribution, let's say the representation of the phase space, is a Fokker-Planck equation, which describes the quasi-probability distribution undergoing drift and diffusion. And we noted that that probability distribution arises, we know, in classical statistical physics when you have a particle that's undergoing random walk. The motion that a particle, a classical trajectory would undergo is Brownian motion, okay? And that Brownian motion is arising due to for example, one way we could get such a equation of motion is if the particle is undergoing random collisions with, say, a fluid. So there's some fluid which has particular constituents, and in a statistical sense, we have an equation of motion. That is to say, this is not a usual kind of differential equation. This is what we call a stochastic differential equation. In that we treat in this formulation the momentum and position as random variables, right? With some random value at every time, according to some probability distribution. Okay, that probability distribution evolves according to the Fokker-Planck equation. But any individual trajectory, so the probability distribution evolves deterministically. Okay, but any one of the variables that it's describing is a random variable, which evolves in some way randomly. Not necessarily completely randomly, it has some sort of, probability distribution around some mean. And the way we might model that, although this is not a mathematically well-defined equation as they've written it, and we'll talk about this a little bit more probably in the coming weeks, is as a Langevin equation, where this is the mean force that is the mean action of these molecules on the particles. It gives rise to viscous motion, that's a viscosity or drag. And then the fluctuating force, so this, or the Langevin force as this is called, is a random force coming from the fact that the collisions happen in ways that we're not modeling completely, we're just modeling statistically, okay? So if I think about an ensemble average, or average over some distribution of possible forces, let me use the notation, not to, I'll just change notation slightly from last time, not to be confused with the quantum mechanical expectation value. Use a double bracket here to say average over the distribution of the possible forces. So this is my average, and this is 0. So this is why it's to say it's the mean forces given here. And then there are fluctuations around the mean. And if we make the Markov approximation, then this is delta correlated. And that's what a Langevin force is. So this is the Markov approximation. And that's the approximation that we've talked about many times now, that, excuse me, is making the assumption that the correlation time of the particle with the molecule that collided off of it is much smaller than the time over which this thing starts to damp. And the reason it loses the correlation is because it's colliding with all the other molecules, rethermalizing extremely quickly. All right? And the strength of the correlation is proportional to the diffusion coefficient. And we saw that because when we looked at the solution to the Langevin equation, what we found is that the fluctuations in momentum underwent diffusion for short time. So this if I wrote it like this, 2 gamma T, 2 gamma T, right? So this undergoes diffusion for a short time, and in steady state, I reach equilibrium, okay? And when I reach equilibrium, that tells me what the diffusion coefficient is, and I ended up with a relationship here that says that the diffusion coefficient was related in this to the damping coefficient through this relation, which we said was a form of the fluctuation dissipation theorem. Okay. So, this formulation of a open system, that's to say this is the dynamics of, say, the motion of this particle in the presence of the reservoir, where we're not tracking what's going on to the constituents of the reservoir, we're just looking at what the particle itself does, gives us a way of thinking about a Heisenberg picture evolution in quantum mechanics for open quantum systems. And that's what we're going to talk about today. Yes, sir?
I think this might be important for later on, but I want to make the distinction between like the Langevin equation and the Fokker-Planck equation.
Yes.
So like the
yes,
Langevin
let's
equation
do that.
Is for, it could describe like the properties of one random walker. We could say like how far it goes in a certain amount of time from like the origin, and then the Fokker-Planck equation is like a distribution of random walkers.
That's correct.
Okay.
Thanks for that question. Let me try to emphasize that more. So we have what we're calling a stochastic process. So there's something random happening, okay? And so we're treating the random variable, either x or p, these are random variables. At some time. Now, the fact that they're random variables means we can associate a probability. So we can ask, for example, what's the probability that I'll find the particle at phase space coordinate x and p at time t, conditioned on, say, it was at some x0, p0 at time t0. So this is the probability distribution. Okay, and there's a general theory of stochastic processes in classical statistical physics, depending on the kind of noise there is. So if we have what we call a Wiener process, which is related to diffusion, we have a certain kind of evolution. We have Uhlenbeck, such or other process, there's another kind of evolution. So we can look at the dynamics in different ways. We can ask, how does this probability distribution evolve as a function of time? Given some initial conditions for the problem. And this, in the Markov approximation, evolves according to the Fokker-Planck equation.
So x of t and p of t evolve according to the Langevin equation.
That's right.
And that probably, okay.
So this, the equation of motion for the probability distribution can be deterministic, all right? So that we found evolved according to a PDE that had no noise in it, because the probability distribution is the noise, okay? Whereas these guys evolve according to the Langevin equation. And what, for example, we saw in we could use either formulation to calculate quantities of interest. So, for example, we could ask about how does, and of course I really, to be consistent, everything should have, the doohickeys here. We could ask, how do different moments of the distribution evolve as a function of time? How does the mean x and the mean p evolve as a function of time, or the fluctuations, or the third order cumulants, or any moments we like? And we can derive the equations of motion for that either way, right? I could, and we did that. We got exactly this result by looking at, for example, the mean p at time t, was equal to the integral over x and p times, the Wigner function, or the probability distribution, if we like. We wanted to write it in this way. So this is that, and then we can use the Fokker-Planck equation to see how this evolves from this stripe. Or we can, as we just did here, use this the Langevin equation to get that. Yeah?
Will that probability distribution be similar to what the distribution is for the fluctuating force? Like
No.
No?
No.
Okay.
They're different.
They're different.
They're different objects.
Okay.
Yeah, they're different objects.
Okay.
They have different randomness.
Okay.
Now, I just wanted to draw your attention to one thing here. We can think about these two different formulations of the problem as the classical analog of the Schrödinger picture and the Heisenberg picture. Why do I say that? So in quantum mechanics, what is the Schrödinger picture versus the Heisenberg picture? How would you, what's the difference between them?
You can say the state of motion.
Right, so we have an evolution of the state or the wave function. That's the Schrödinger picture, right? And so if I wanted to ask, how does some, say, mean value of some observable evolve as a function of time? Let's say this is some function of x and p, then I can write this as, well, let me say, okay, there's different ways I can write this. I can write it in the wave function language. Let's say this was a as a function of x. Then this would be this, right? Say this is like a potential or something like that. And what you see is I have the observable and the probability. Of course, if this is some operator which is a function of x hat and p hat, then I can't write it in that, but I can write it in the Wigner representation, where the Wigner function is just the representation of the state in phase space, right? So this is the Schrödinger picture. It's the representation in phase space, but it's the Schrödinger picture. The state is evolving as a function of time, and using that I can calculate, which is to say the state, which is the thing that tells me the probability of getting certain outcomes, evolves as a function of time. Whereas in the Langevin formulation, we're looking at random trajectories. There's the observables evolving as a function of time. So classical mechanics is no different than quantum mechanics, in that I could have these two formulations. In the closed system formulation, I either have Hamilton's equations of motion, which tell me how x and p evolve. They're the differential equations for how the canonical coordinates evolve for time. Or the Liouville equation. The Liouville equation is not something we typically deal with in classical mechanics, because typically we think about classical mechanics as deterministic. But I could also formulate classical mechanics where I don't have complete information about x and p. It's classical randomness, but it's still randomness. And I would say there's some probability distribution over, and this evolves according to a Liouville equation, which would have both a commutator, or in this case a Poisson bracket with a Hamiltonian, plus dissipative terms, which would be the Lindblad terms, which in the classical would be the Fokker-Planck. So this is just two different ways of formulating the same problem. Okay. So with that, and thank you for that, let's now turn our attention to the Heisenberg picture formulation of the open quantum system. We know the Heisenberg formulation in the closed quantum system context, but now we want to talk about it in the open quantum systems context. So what we were discussing last lecture, so again, we're talking about the Heisenberg picture formulation of open quantum systems dynamics. What we discussed last time was that we are we're forced into a Langevin formulation. In classical dynamics, although the fluctuating force might be there, so let me just say, so classically, we have this. Right? Now, when you think about, maybe when you solved, in freshman physics or junior physics, when you looked at a damped motion of a particle moving in a viscous fluid, you didn't necessarily include this term, right? You would just have this. And it wasn't really required by anything fundamental that that fluctuating force was there. It arises when the drag is coming from discrete processes. I mean, if it was a continuum fluid, there would be no fluctuating force. It would just be drag. It's the randomness of these discrete kicks that's giving rise to this. Moreover, this fluctuating force might be absolutely tiny compared to this, especially depending on the temperature that we're talking about. And so the action of the fluctuations on top of it might just be completely negligible, and we just neglect it. So in lots of cases, we just typically neglect this in our discussion of damping of a particle. But if I think about this quantumly, we run into problems. So quantumly, and I love having quantum as an adverb. If we try to write down, say, the amplitude of an oscillator, we tried to write down an equation that looked like this. This was the kind of our, right? This equation on the mean is true. That is fine. Okay, smiley face. On the other hand, if we wrote down a Heisenberg picture type operator equation for that, then the solution to this operator equation has some major problems. Because if we look at that equation, then the commutator of A with A dagger at a later time decays. In fact, goes to 0 when this is big. And that's bad, because that would mean a violation of the uncertainty principle. In fact, the uncertainty principle, we know, must be always true, and it is maintained if the overall evolution is unitary. Okay? So if the overall evolution of the system and everything else is unitary, then whatever, if I have some commutation relation between two observables at time t, right, then that is, according to the Heisenberg evolution, that, right? And if I multiply that out, this times that minus the other way around, then the UU daggers in the middle cancel. And that's equivalent to this. Okay, so if this is some, if this is turned out to be a constant, then it's going to constant at all times. And if it's some operator at time 0, then that's whatever that operator is at time t. And that's then would, in the case of x and p, preserve the uncertainty principle. And this kind of evolution does it. Okay? Now, the way to deal with that is to write down the Heisenberg equations of motion for the system and reservoir together. We must include the reservoir in the evolution of the total system plus reservoir. Now, in the Schrodinger type picture with the state, we traced over, but there's no equivalent of doing that in an operator formulation. Okay? If we did that, we don't have a kind of partial operator, a marginal operator. That's the problem. So to deal with this problem, what we do is in a Heisenberg picture, in this kind of Heisenberg picture formulation, I'm going to let this, what we do is include the reservoir. Bless you. In the total evolution. And that overall evolution is unitary. Okay? And what we will see in doing so, when we make the Markov approximation, is we get a Heisenberg picture that is a Langevin equation. And this is known as the Heisenberg-Langevin equations. So that's what we're going to do. So unlike in the classical mechanics, where we didn't really, we can neglect this. In the quantum picture, we can't. It has to be there. In some sense, because the quanta are discrete. And so there is always a fluctuating force. Even at 0 temperature, there is vacuum. And that vacuum has corpuscular nature. It has discrete photons, and there always are quantum fluctuations, and they cannot be neglected. Otherwise, we would screw up the Heisenberg equations of motion, the Heisenberg equation principle. All right, so let's see how that goes. So we're going to formulate that. Let's come back to the main board over here. Let's look at the specific example of our damped oscillator, although the procedure, as we will see, can be generalized. So let's go back to talk about the damped semi-harmonic oscillator, which we formulated in a simple system reservoir picture where our Hamiltonian had the Hamiltonian for the system. So we're going to have this is our oscillator, that's its Hamiltonian. Ignore the plus 1/2 is irrelevant here. Then we have the reservoir. The reservoir in this case are a bunch of other harmonic oscillators that this main oscillator is coupled to. So we have a bunch of other oscillators labeled by some index K. We'll call those B. And then we have a linear coupling in wave approximation, okay? So that's our very simple model, coupled oscillators that lead us when our reservoir of oscillators is in some thermal state, even at 0 temperature, to a damped oscillator, okay? So we didn't go through the details, but we sort of sketched out how one could use this to get equation, the Lindblad equation, for the density operator in the Born-Markov approximation, in the same way we did it for the two-level atom decaying in the vacuum, okay? But now we're going to look at the Heisenberg picture, but including both this, so this is my system, and this is my reservoir, which are all the other modes that this guy is coupled to, okay? So let's write them down. The Heisenberg evolution of A, we got to do minus I, the commutator of A with this, gives us minus I omega naught A, minus I G D sub K, sum over K. And each of these modes of the reservoir evolve according to its equation. Right? And this actually, no, this one doesn't have the sum because there's only one K that doesn't compute with, right? We pick off that K. All right, so that's the equation of motion. We typically, to solve this, will go to a rotating frame to get rid of the free evolutions, like the interaction picture. So let me define A tilde such that A hat of t is A tilde of t e to the minus I omega of t. So this is my slowly varying which is the damping is going to be slow compared to this big frequency. Okay, so if there was no damping, this would just be constant. But because of damping, this is going to evolve, but slowly compared to omega naught. So I'll factor out that. So that means that A tilde is A hat e to the plus I omega naught t. And the equation of motion for A then is plus I omega naught A tilde, I'm sorry, yeah, A tilde plus e to the I omega naught t dA hat dt. So now I can plug in for A hat there and get the equation for A tilde. Says that dA tilde dt is equal to minus I k dk dk e to the I omega naught t. It just factors, it cancels this guy, cancels this guy. Plug that in. Okay? Alrighty. So, now what? Well, to get somewhere here, I can take this equation and write a formal solution. So what we have there is bk of t is equal to the solution to that equation. Well, I have the initial condition, and then I have the forcing term, and that gives me minus I gk integral from 0 to t dt prime. That guy's got a star on it. And then a of t prime, a hat of t prime is a tilde of t prime e to the minus I omega naught t prime. Okay, that's just the formal integral. Well, I have to go of t minus t prime. Yep. Then if I take the derivative of that, I get that equation. So now I take this solution and I plug it back in here. All right, this term first, and that gives me minus the sum over k, gk squared. And that should be omega sub k, excuse me, not omega 0. E to the minus I omega naught minus omega k t minus t prime a tilde of t prime minus I sum over k g sub k e to the minus k dk at 0. Okay. All right, so that's just a formal integration of that equation. But we've seen this before. It may not seem so familiar, but we saw equations of motion that were similar to this when we solved for, in the Wigner-Weisskopf approximation, for the evolution of the probability amplitudes of the couple modes to the two-level atoms. So, firstly, this operator here is what we're going to call f of t. This is what we call the noise operator, or the Langevin operator. In fact, we see something that's coming close to the Langevin equations of motion. There's something here, we don't quite yet have it, that is like a damping of the oscillator, plus some source term here that depends on the reservoir variables, right? This variable depends on the reservoir variables, not the variable itself. All right, so now what? Well, I lost my integral, didn't I? Yeah, good, it better be in there.
And I think you also lost omega naught in the second expression. The second.
Where did I lose an omega naught?
No, here. The F15. If you put in.
Oh yeah, I do. Thank you. Okay, great. So let's do that. Omega naught minus or
Omega.
yeah, omega minus omega. Let's try it. Minus omega k minus omega naught t dk at 0. Yes, indeed. And this should be minus this the integral from 0 to t prime sum over k gk squared.
And the plus on the
Over here? Yeah, we're writing it the other way around. Doesn't matter. But yeah. Okay, good. So now this equation is of the form where this kernel is there. So this is of a general form of a coupling of a reservoir to the system, which in principle has some memory effects that we know. It says that what happens to the observable at some time t depends on some history. However, what we make is the Markov approximation, which is the approximation to say that this variable, this falls off, so this has some correlation time. So this thing goes to 0 when this is sufficiently big compared to the correlation time. Okay, so this goes to 0 when that is true. So what we did in that case is we said, well, as long as the time that we're looking at is sufficiently long compared to the correlation time, in the Markov approximation, we took that to t equals infinity. Because it doesn't really matter what t is, as long as it's sufficiently big compared to the correlation time. Right? But of course, it's still supposed to be small compared to the time scale over which this is changing. That's to say, we're looking at times that are t that are huge compared to the correlation time, but much, much smaller than the rate or the time scale over which the particle damps. So, under that approximation, this is exactly what we did in the context of the Phys581 approximation, and when we looked at this again in the formulation of the Lindblad equation. What we said then is that the integral is approximately equal to that is to say, this thing is basically a delta function in time. Any time t prime that's minuscule different, this is 0, because that correlation time is tiny. Okay? So we treat it like a delta function and pull it out. So now this becomes equal to the integral 0 to t, 0 to infinity, of the sum over k, gk squared, e to the minus I, omega k minus omega naught, t minus t prime. And then that is the same thing as our integral d tau. So we can turn t prime, we call this tau. The same limits of my integration that I care about And my integral then, e to the minus I omega naught minus omega k tau is equal to our half of the delta function minus I Cauchy's principal part omega k minus omega naught. Okay. So with that said, what I get is that the evolution of this, of the mode amplitude is equal to minus sum over k pi k gk squared delta omega k minus omega naught a tilde of k plus, actually, I'll put in the whole thing, minus I Cauchy principal part sum over k gk squared omega k minus omega naught a tilde of k plus f. Okay, so what is this? This is Fermi's golden rule. This is half, I mean it's 2 pi is Fermi's golden rule. This is gamma over 2. Okay, so this is the damping rate that comes from Fermi's golden rule when perturbation theory, when this oscillator is coupled to this, it's interacting with this reservoir. That's what this is. And this is what? I don't know. Well, first of all, it's got minus I in it, right? So this means is related to a phase rather than a damping, right? So what does this represent? We've seen it before.
That's what the Rabi one is that?
Sort of the Rabi one. Remember, in the context when we had the atom interacting with the black body, what did we see there in addition to damping? We had the light shift, right? We had the shift in the energy of the atom due to its being perturbed by, and that's what this is. This is a shift in the energy of the oscillator due to its interacting with it. And we know that's true. I mean, when you have an oscillator, its frequency is shifted, its resonance is shifted by the damping, right? So this is delta E over H bar, which we typically just absorb into the new value of the resonance frequency, omega naught. So omega naught, if you like, is renormalized by its interaction with all the vacuum modes. Okay. So what we find, then we can call this delta omega, is exactly what we expected to see. So let's just neglect this. I mean, it's there. We can redefine omega naught to be omega naught plus delta, and it's just a shift in what the resonance frequency is. That the amplitude operator satisfies So what we have in this equation, we have damping and a noise operator. The noise operator here is an operator that acts on the reservoir. In some sense, this equation saying that the system and reservoir are being coupled, the Heisenberg equations of motion, I mean, in the Schrodinger-like picture, the state, what we saw is the state became entangled. That is to say, the degrees of freedom of the system became entangled with degrees of freedom of the reservoir. In the Heisenberg picture formulation, we see that entanglement is indicated by the fact that the operator for the system at time t depends also on what the operators of the reservoir are at that time. They're correlated, okay? So, let's firstly say a few things then about this noise operator. Let's look at its correlations in the same way that we looked at the noise correlation. We have the fluctuation dissipation theorem classically for how the Langevin force is correlated. So let's look at, for example, a two-time correlation function where this is an average over the reservoir, okay? Which is the modes of all the other oscillators, the B sub k oscillators. So this is equal to sum over k and k prime, gk, g star k prime, e to the minus I omega k minus omega k prime minus t minus omega k and t prime e to the I omega naught t minus t prime times bk dagger bk prime over the reservoir. Right? What is that? Well, firstly, it depends what the state of the reservoir is. Let's say we have a thermal state of the modes of the reservoir. What is this correlation function then? Or this expectation value? By the thermal state, as we've discussed, it's diagonal in the number basis. So this thing is 0 unless k equals k prime. And when k equals k prime, it's the mean number of excitations in that mode. So it's the thermal distribution at times delta k, k prime. Right? Where that bar is over the thermal distribution, the Planck distribution. Right? So now, to piss you off, I'll just erase this and make this t minus t prime with one sum. And this is the same kind of function we saw just a moment ago when we were just, doing those integrals and so forth. If we go to again, this usual formulation where I turn this into a density of states, And the usual thing that this thing is very small unless t equals t prime, maybe it'll make it not, I get, again here, I will get the same factor of gamma here, gamma times n bar at omega naught. This is the Markov approximation. So I have delta correlation of the noise in the Markov approximation. And if I look at this in anti-normally ordered form, then I'm going to have a B dagger instead of a B dagger B, which commutes and gives me an n plus 1. This again is a form of the fluctuation dissipation theorem. Where these coefficients are related to the diffusion coefficients for a dagger. One of these should be a dagger, otherwise this makes no sense at all. Those guys are 0 because right, b squared or b dagger squareds, their correlation function would be 0. Let's just quickly see that this gives us the diffusion coefficient that we saw for the momentum. So let's look at the quadrature P. What's the equation of motion for that in this Heisenberg-Langevin formulation? This is the quadrature, say A minus A dagger over I root 2, right? So that's equal to what? That plus a dagger, well, the first term, that's real, so that's that for the first term. And then the second term I'm going to get plus F plus, or minus, sorry, F dagger over I root 2. Right? And I'll call this F sub P. So let's look at the time correlation, two-time correlation function of that. That's going to be equal to 1/2 F of T, F dagger of T prime, plus F dagger at T, F at T prime. Because all the two other cross terms, they'll call it F squared and, or FF, F dagger, their correlations are 0. Right? Because they involve B daggers, I mean T dagger, P dagger, and B squares, and in the thermal state, those are 0. So this then gives me n bar plus 1/2, which is exactly the diffusion coefficient that we saw in the Fokker-Planck equation. It's the expected way in which, in a thermal state, we get diffusion. And in fact, let's see that this gives us what we saw in, we get the expected equation, or diffusion coefficient. So this is equal to the twice the diffusion coefficient for momentum. I forgot sure to have the delta function in there, sorry. So in the high temperature limit, n bar is equal to that. Right? Well, that's not high time. It's high time that I learned how to write. It's high temperature. Right? That's the mean number of photons. So that would say that twice the diffusion coefficient was equal to, oh, what happened to gamma? Plus a half, I have to write gamma in there. Now it makes sense. Gamma times n is equal to gamma. Well, what did we have in the classical case for our diffusion coefficient? What we saw before classically, what did we have? I wrote it at the beginning, was the mass times gamma times kT, right? And this was the diffusion coefficient for the momentum. This is in dimensionless units. So if I want to find this in dimensionless units, I have to divide by the p squared, because this has got the units of p squared, the characteristic unit. What is that for a harmonic oscillator?
H bar n squared omega.
M times h bar omega. Right? So that cancels, and I get the right thing here. Right? Because when I divide this gamma over 2, this is what we call gamma. So indeed, it's all in agreement. Now, let us show, importantly, that this equation correctly preserves the commutation relations. That is to say, we preserve the commutator through the noise operator. So if I look at the solution to this equation, that's the formal solution. Okay. So let's look at the commutator of that with that, which of course is the same thing as in the lab frame, because when you put back in the e to the minus I omega t's, it would make a difference there. That would be the same. And let's plug that in. What I'm going to get is the commutator of this with that. That gives me e to the minus gamma t that. This commutes with this, because these are the mode of the reservoir operators, and these are the systems they can use. But then I have to have the commutator, so I'm going to have an e to the minus gamma t here, commutator oh, I gotta have this guy, either the minus over 2 t prime plus t double prime. Okay, so I plug that in, plug in the noise reservoir that I had before, and I get, I'm going to have a commutator. Instead of having the expectation value, let's just write it down because too many steps in my head, I'll get it wrong. This was equal to minus I g k e to the minus I omega k 0 t dk, right? And times 0. That was the noise operator. So what's the commutator of this with itself at 2 different times? Well, these guys, the commutator will be 1 only when k equals k prime. Okay? And then that will, then the f with f dagger will cancel, and I'll get the commutator of this is equal to sum over k gk squared e to the minus I t minus t prime, or in this case t prime minus t double prime. Okay, and that comes to the fact that b with b dagger commutator is 1 only when k equals k prime. Okay, what's that? Well, it's the same delta function thingamaboosit, but now without the n bar, right? So this is equal to gamma delta t minus t prime minus t double prime. Okay. So, plugging all of that in, I can integrate over t double prime. Yay. Okay. Now I can do that integral. This is equal to 1. And this is equal to e to the, oh God, I got this backwards. Minus times minus is plus. Now it's nice. Gamma t minus 1. Because I integrate to gamma. And I get e to the minus times that, that's 1. This times this is minus that. Et voila. 1. So, the moral of the story here is that the noise operator is required to replenish the quantum fluctuations that are being attenuated. They have to be there, otherwise you wouldn't satisfy the uncertainty principle. Now, we saw exactly this kind of equation in a homework problem. When we talked about attenuation in a coarse model, where we looked at a beam splitter as a way of accounting for attenuation, right? So, if I have, classically, if I have a beam splitter and I send in some field E, then what comes out is some attenuated field with some transmission coefficient. Okay? If I try to do the same thing quantum mechanically, there's something wrong there. Because if I look, this is called E in, this is my E out, this is my A in, this is my A out. Because this would not preserve the commutation relation. If I look at A out with A out dagger, that's equal to T squared, which is generally less than 1, unless there was no beam splitter there at all. So that's bad. This is not a proper transformation. Well, why not? Because it's not unitary. How do I make it unitary?
Complete the vacuum.
There's another mode here, right? And this other mode, let's call this, so this is B in, says that A out must include, in addition to, in the Heisenberg evolution, how this gets, but also the coupling of that. This is my A out. Right? And now when I look at that, what I get is that this is equal to R. And if this is a lossless beam splitter, I mean, you know, if there's absorption in it, I better put in another Langevin operator to represent what's going on with the loss if there's absorption. If this is not, if this beam splitter has absorption in it, I better put it on. This is 1. So this is my noise operator. And this is like my e to the minus gamma t. And the commutator, what we see here is that if I have A out is some eta A in plus F, that there's a requirement here, this guy has to satisfy certain commutation relations. That's to say, the commutator of A out with A out dagger is 1 is equal to eta squared plus the commutator of F with F dagger. Which means that F dagger has to equal 1 minus eta squared. We have, and if the magnitude of eta is 1, well, that's perfectly fine. Then I don't need this. That's unitary, right? But otherwise, I must include this noise operator in order to preserve the quantum taper. And we see then that what's going on here, whenever, to make this, because this is a unitary transformation, the quantum fluctuations in the reservoir, in this case this is a one-mode reservoir, replenish the attenuation of the quantum fluctuations that are happening here in order to be consistent. Now I just want to make one last comment. We don't really have time, and I'll just, it'll be in the notes, but we'll just leave it here for now. This is also true if this not represented attenuation, but suppose that this represents gain. Suppose I have an amplifier. I take a photon, I put it through a fiber amplifier. I try to amplify my signal, right? So suppose that eta is real and positive and greater than 1. If it's greater than 1, this represents gain rather than attenuation. But what this tells me is if I have gain that is of this form, it must introduce excess noise. It can't just keep the signal to noise ratio constant. If you increase the signal, you don't just increase the noise, you add excess noise in the process in order to maintain unitarity. And this is a well-known thing to laser people, that you add excess noise if you have an amplifier. And it's due to quantum mechanics. You can't get away. Now, you could get away with it if you didn't have an amplifier that was the same for all quadratures. If you had a phase-dependent amplifier. So let me show you one last thing of an example of an amplifier which is noiseless. Let's suppose A out is equal to cosh R A plus sinh R A dagger. Now, if I look at this, if I look at X out, that's equal to A out plus A out dagger over root 2, which is equal to cosh plus sinh A in plus A in dagger over root 2, which is e to the R X in. So this is amplifying this quadrature. However, if I look at the other quadrature, it will de-amplify. So it depends on the phase quadrature. But it's noiseless. That is to say, if I look at the fluctuations, this preserves the commutation relations. There's no excess noise here. So what we find is the following. If I have a phase insensitive amplifier, that's to say I send in some laser beam and it amplifies the amplitude the same way. No matter what the phase is, I get the same amplification. Then what happens is the following. If I start with some arbitrary phase, then I start with, say, some noise. This is my alpha. I'll get, the alpha gets amplified to some gain times alpha. And the noise, if it was kept the same signal to noise ratio, would look like that, but I get excess noise. So this is G plus a half, it turns out, alpha. I get excess noise if it's phase insensitive. If I have a phase sensitive amplifier, I can be noiseless in the sense that I preserve, so I start with the coherent state, and what do I get when I put this in a parametric amplifier? That's to say a phase-sensitive amplifier. I'm going to get a squeezed state. So what's going to happen is this quadrature is going to get amplified by exactly the same amount, So now this is G times a half. This is G times alpha. But this quadrature is de-amplified. If I had sent in a different, this is if I phase matched exactly here. So what we learn here is that amplification generally comes with excess noise. That excess noise is there from quantum mechanics. But I can engineer it to be noiseless, that's to say, preserve the signal-to-noise ratio at the expense of having a phase-sensitive amplifier. That's to say, my amplifier in this case might be, I have some pump, and that pump has some phase associated, and then I send in a signal, E, and there's the phase of my signal, and whether or not this gets amplified or de-amplified depends on the phase of the signal relative to the phase of pump. So it's a more delicate kind of amplifier. Depends on the phase. Okay. All right. Very good. I will be loading those notes soon. This concludes what our discussion of the damped oscillator, and what we're going to spend the rest of the semester talking about is the theory of quantum trajectories and continuous measurement. All right? This should be fun. All right. Take care.